So in this video, I go about finding how to compute the area of a region that's defined between two curves. I also go and show you how to find the net change of a function in terms of a definite integral. For this development, I'm going to show you how to find the area between two curves by using a Riemann sum. And we'll use a simplification of it where we assume that we take the interval from a to b and divide it into n equal length subintervals. That way we don't have to take the limit as the norm of the partition goes to 0. We just take the limit as n goes to infinity. In every single interval, we'll still pick an x value in order to get the height of our rectangles. The summation of the product of the function value at our choice point times the width of the interval, that would then be the area, and the summation is adding up all those areas. That would then be a Riemann sum. The limit of that Riemann sum should then equal the definite integral from a to b of f of x dx, assuming the function is integrable on that particular interval. So in general, if you want to find the area of the region bounded by a bunch of graphs or axes, good idea to start with is to graph the region first. Then to find any points where these curves intersect, as they often help define the borders of this region. Then take the object and crush it to an axis, either to the x-axis or to the y-axis. Imagine like you're projecting it, like you're flashing a light upon the object, and the shadow is then going to hit one of the axes. That is the interval you're going to partition. Now, once you have that, for every single subinterval, we'll form a bunch of rectangles. For every subinterval, we'll pick an x value. That gives you the height of the rectangles. We'll then take the sum of those rectangles. And the limit, we'll then get an integral. So, doing it with the region that you see here between these two curves, I crushed it to the x-axis. I then partition it into pieces, and for each of those pieces, I define the height of a rectangle and a width of a rectangle. The height is found just by, if you look at any single point in the subinterval, pick one such x value. That will then give you a value on one function and a value on the other. That difference is then the height of the rectangle. So using that one rectangle, you could then find the area of that one rectangle by taking the difference in the function values at one x value in that interval. We then multiply it by the width of the interval, which is the change of x. We just do that for every single rectangle. So then the overall area of the region I'm interested in is about the sum of these areas. But that's a Riemann sum. So then to find the limit as n goes to infinity, assuming f and g are both integrable and they're continuous, so they are, the area then is just the integration from one bound to another. And in this case, the bounds appear to be from -3 to. Finding the area of a region by doing what I just showed you would be time consuming because you have to write down lots of rectangles. Instead, notice they all have the same pattern. To find the area, you just find the height of the rectangle, then you multiply it by the width. So we'll use one rectangle in our picture to represent all of them. We typically use a really thin rectangle or even a straight line to represent one of these things. That is called a representative element. Here's an example of doing so. Here's the region. Here's me projecting it upon the x-axis so I know the interval I'm partitioning. I then draw in one rectangle and I think of that rectangle as moving left to right. So it has a thickness of a change in that variable, which would be dx, and it moves left and right with the x value. Now the height is found by looking at the 2 points that define the top and the bottom of this particular rectangle. Those 2 points have y values. It's the difference in those y values that's going to give me that height. You have to find the height as a function of x though, because you're going to take the height times the dx to get the area of that rectangle, and then you'll sum up over all of those possible rectangles as your x varies from the left from A to the right at B. In the previous slide, I showed you how you could make a rectangle that is vertical, standing up on end, and it would then slide left and right to sort of sweep out the entire area. You don't have to have that though. Your rectangle could be instead oriented horizontally and move up and down with a changing y value. To show what I mean, here is another weird region. Now, if you think about taking the object and crushing it to the y-axis, giving you the interval from C to D, and then drawing in a rectangle that has a small change in y, where the rectangle would move up and down with that y value, you can find the height by finding the ends of the rectangles x values. So those 2 points will have x coordinates. It's the difference in those x coordinates that will then give you the height of that rectangle. But you must find the height as a function of y as you're accumulating by integrating through y. So the area of that rectangle will then be the height as a function of y times dy. You would then sum up over all those rectangles areas as y ranges from c to d. So you have two different ways to basically compute the area of a region between two graphs. If you have two functions f and g, which are both integrable over an interval from a to b, and you're trying to find the area of the region between those two graphs where the values of f are more than the values of g, or at least equal to them, over that interval, it's just the integration from a to b of the difference in the two functions, larger minus smaller, times dx. If the area of the region is defined to be between the graphs of x equals f as a function of y, and x is a function of y, where the function f values is always greater than the function g values over the interval of y values from c to d, then you just find the integration from c to d of the difference in the function values, larger minus smaller, dy. Now notice that the region then is very, very strict, that in each case one function value is always greater than the other. If you have a region where the region is bounded by two curves, but in some cases one function swaps going above and above the other, you can't use this integral. It's slightly more complicated. You have to break that problem up then into multiple problems. So in general, since we have two different techniques, how do we go about finding the area between two graphs? First, you should always sketch the region. Use your calculator to do so. Next, decide upon which of the axes you will project the region on. That then determines the interval that you're going to integrate over and also the variable that you'll integrate with respect to. Next, for some of those either x or y value, depending upon which axis you project it upon, sketch a tallest possible thin rectangle in that region that is perpendicular to the interval at this x value. It will then move back and forth, or up and down, with the changing x or y value. Just remember the following things though, that whatever you projected upon, the integral in the end must be entirely in terms of that variable. That means even the height must be in terms of that variable. But the height will always be in terms of that variable, but to find it, you have to find the other variable's values for the points that are the end of the interval, or the end of your rectangle. Finally, as you're doing this integration, if you look as your rectangle would move left or right or up or down, if the points that define the top and the bottom, or the right and the left, ever swap, well, that means that you have to find a whole nother integral just to find the area of that new portion. So let's set up an integral that describes the area of the shaded region bounded by the curves x cubed and 4x in the first quadrant. So I have already gone and drawn the region for you between these two curves in the first quadrant, but let's go ahead and find out where they intersect at this point and at this point. To do so, that would mean that they would have to have the exact same y value, and in solving that equation you get x cubed minus 4x would then be 0. So x times x minus 2 times x plus 2, that would be 0. And we get x is plus or minus 2 and 0. So we have then 0 and 2. If I then project this region upon the x-axis, I would then get this interval right here. Now for that interval, I'm just going to pick an x value. There it is. For that x value, I'll then just draw in a rectangle. That rectangle will move back and forth with the x value. Let's put an x on the inside. It then moves back and forth, left and right, as the x value changes. There's a point down here at the bottom, there's a point up here at the top, and those points have y coordinates that I need because the height as a function of x will then be a difference in the larger y value minus the smaller. So I have to find out what those y values are. Clearly this point, as the x value changes, this point will always ride on this graph like it's a car on a railroad track. Now that means that this point is always given by the formula y equals 4x. So this is y equals 4x. For the same reason, notice as this x changes back and forth, see how this point is always riding the lower curve? So I always have the exact same formula for y in terms of x, and that would just be x cubed. So the height would then be the larger one, 4x, minus the smaller y value, which is x cubed. So the area then is the integration from 0 to 2 of the height, which is 4x minus x cubed dx. And you can easily integrate that. That would just be 2x squared minus 1/4 x to the fourth, and we evaluate that from 0 to 2. So if you plug in 2, you would get 8 minus, that would then be 4. That is 4. So the area of that region is 4 units. Let's try that again. Once again, I'll take this particular region bounded by these two curves, and I want to find a integral that describes the area of the shaded region. Now I'll try first by finding out what are these intersection points that help define the edges of this region. So that we got a point right here, and you get a point right here. So to do that, that would mean that the y values would have to be the same, or the x values have to be the same. I'll take this x, and I'll take this, and I'll plug it into here to get that y would have to equal 4 minus y squared plus 2. That means that y squared plus y minus 6 would have to be 0. That means y plus 3 times y minus 2 would be 0. So we get the y coordinate of the point would then be 2 or negative 3. I now know the y coordinates of those points. I can then find the x coordinates easily because from this equation right here, I have that x is y minus 2. So this point, its x coordinate, when y is 2, the x value is 0. And this point down here, when the y value is negative 3, the x value is negative 5. Alright, so I have those points. Now in order to find the area between them, I have to decide which way am I going to project the object, upon the x or y axis. If I project it upon the x-axis, then my rectangle would have to go like this. And it would move back and forth with the next value. But notice if it did that, do you see how the top would always be on this curve for this portion? That's one function y in terms of x. But then suddenly, once we get past x equals 0, now the top of my rectangle will be on an entirely different function. That's a different function y in terms of x. If I use this orientation for my rectangle, if I project the object upon the x-axis, I'll have to do 2 integrals. But I don't want to do that. So let's go ahead and make a rectangle that's nice and long. And it's defined then where it meets here at the edges. And it moves up and down with its y value. Now I'm going to need this point's x coordinate. I'll need to know this point's x coordinate in order to find the overall height of this rectangle. The width of that rectangle is dy. So this x coordinate, well, notice as the rectangle now moves up and down, see how this point always stays on the same curve and is always to the right of this point, because as the rectangle goes up and down, this point rides this curve. This seems like a good way to set up the problem. To find those heights, I need to know then what is this x coordinate. Well, we know though that this point is always on that curve, so the x is given by 4 minus y squared. On the other hand, this point is always on that curve, and if you solve for x, look, I already did that for you, you'll notice that x is just y minus 2. So the height as a function of y is the larger x value minus the smaller one. So that's the larger x value as a function of y minus the smaller one. So that would then be 4 minus y squared minus y minus 2. That then is 6 minus y squared. So the area then is, it's the integration from a y value to another y value of the height, 6 minus y squared, times its thickness, dy. I'm summing up the areas of the rectangles. All I need to know now is what's the interval that I go over. If you take the object and you project it upon the y-axis, you'll go from this y value to that one. That range of y values is the y value of this point to the y value of that point. So the integration is from negative 3 to 2. And that's it. That's setting up the problem. This time I won't do the integration. Notice that the most difficult thing here is not actually doing the integration. The challenging thing really is setting it up in the first place. As another example of how to use a definite integral, it can describe the net change in a function. Now, if you're given a differentiable function f, then the derivative of that function, f prime of x, it has an antiderivative. It's just f. So the net change in the function over the interval is just the difference between f of b and f of a. But that's what you would get if you evaluate the definite integral of the derivative of f dx over the interval from a to b. Think of it as this portion gives you the overall change in function value for a change of x, and this is a small change of x, so that this corresponds to then the overall change in y, but only for a very, very small piece in x. When you integrate, you wind up adding up all those small changes in the function value, giving you the total change in the function value. As our last example, suppose you wanted to know if a bacteria colony begins with 200 cells and grows at a rate equal to 2 plus t squared cells per hour after t hours, how many bacterial cells then are present in the colony after the first 4 hours? This is not difficult to do. You think of it this way. Let's say p as a function of t, this will then be the population of cells after t hours. So I want to know what's p of 4 equal to. Well, one way to think of it is to take p of 0, the initial population, and add to it how much that population will change. That's the same as writing p of 0 plus, this would be the population after 4 hours minus the population after 0 hours. Now I know, if you look at this expression, the p0's cancel, giving you p4. So then how can you use this to compute what we need? Well, but this here, that's the overall change in the function value. So that can be given by an integration from 0 to 4 of the derivative of the population as a function of time dt. Thing is though, right here, I told you the rate in cells per hour, and that's exactly what this is, because p gives you cells, t is in hours, so the derivative of p in terms of time, that's the derivative of p in terms of time, that gives you a change in cells per hour. So we know what that function is. So this is then equal to p of 0, that was 200, plus the integration from 0 to 4 of our rate of change, which is 2 plus t squared, and that would be dt. Now I have to just integrate it. So that's 200 plus, that'd be 2t plus 1/3 t cubed, and I evaluate this from 0 to 4. This would then give me the approximate answer. So this would then be 200, and if you plug in 4, you would get 8 plus 64 thirds, and then minus 0, which we won't bother. So it's 200 plus that amount. That's it. All you have to do is just add that up. That'd be the amount of cells. You know, it's just an approximation, but it's a pretty close one. And that's it. That goes about showing you how to find the area of a region between two curves, and that's introducing the net change theorem.